Okay, so thanks everyone for coming back. This is the second of my three parts on model-based derivative-free optimization, DFO. Um, Today yesterday was kind of more generic kind of introduction to the topic at a kind of very high level, sort of applications, motivations, why we care about the topic, and just introducing the basic idea of a trust region method based around constructing derivative-free models in some way, basically via interpolation. So today we're going to get into a little bit more of the weeds of the topic and would show some proofs, for example. So just to kind of recap the key points from yesterday, the problem that we're going to be solving is just a smooth, unconstrained, non-convex problem over Rn. And I'm going to assume that we have a Lipschitz continuous gradient with a constant L, but we're in a DFO context. So although there is a gradient, we're not allowed to see it in the context of our algorithm. And yesterday we looked at the basic idea of mimicking derivative-based trust region methods, which are quite practically successful, and they fit naturally with how we look at approximating our functions. And so the basic flavor was that at every iteration, near our current iterate xk, we're going to sample some values of our function and use that to build probably a quadratic model that's going to interpolate the value of f at those points that we expect to be a good approximation to f at least locally. Given that it's local, what we're going to do is we're going to calculate a step that decreases our model, but the step is going to be constrained to not go too far from where we are now, reflecting the fact that the model is only expected to be accurate in some radius delta k. Once we found something that decreases our model, we evaluate the function at this new point, and we decide, well, the model said it should decrease. Did it actually decrease the true function? And we'll use that to decide whether or not we take a step to that new point and decide how we update our trust region radius. So that was the basic idea that we saw yesterday. So today I want to talk about kind of the classic model-based DFO algorithm and basically derive that and what that ends up looking like, prove its convergence, and then talk about how we go about constructing interpolation models. So these are kind of the basic building blocks, and then tomorrow we'll look at how this kind of gets extended in a somewhat more practical way. This is the basic ideas. So to motivate the first aspect, which is model accuracy, I want to go back to what I mentioned yesterday, where we had linear models for our function that were constructed by finite differencing. So for my given function f, I want to approximate it at iteration k by a linear function that's going to look like a linear Taylor series, but g is going to be calculated by approximating the gradient of f using finite differencing. And yesterday I mentioned that the error bounds we get from this look as follows. So there's an error bound in how close our finite difference gradient is to our true gradient. And that depends on the dimension of the problem, the Lipschitz constant of the true function's gradient, and the size of our finite differencing perturbation h. We also then proved that if the gradient is accurate, well, then the model itself is accurate relative to the true function. And the error bound says that the difference between the model and our true function at a point y depends on something to do with the Taylor error. So the approximation error from a first order Taylor series. So we get something like norm of y minus x all squared. And then an extra term that basically comes from the difference between a true Taylor series and the model that we've got, which has something related to the size of our gradient error times a distance. So we got a expression that looks like this. So we've got a bound for our model error and our bound for the error in the gradients of the model. So in the trust region method, what we do know is that the step we're going to take, we're going to move from xk to xk plus sk, where our step sk is of length at most delta. So if we think about what that's going to mean from an error point of view, well, quite naturally, we'd take this model error bound and plug in our new point into here. Because if I plug in xk, well, I've forced my model to be exactly correct. If y equals xk, the model is equal to the true function value. If I plug in my new point, my error bound ends up looking something like this. So everywhere I had a size of the norm of the perturbation, I just plug in a value of delta. So I get a term that's proportional to delta squared, and a term that's proportional to delta that also depends on the step size h, the perturbation size h. And as I mentioned yesterday, it's quite natural to pick H reasonably small, but not too small that rounding errors hurt you. So a natural choice here is to pick H roughly of size delta K, which means both terms here end up being of size delta K squared. Picking H significantly smaller than that isn't really going to achieve a huge amount more in terms of the error bounds relative to delta, but you are going to run into rounding errors a bit more. So let's say we pick H to be of size delta K. And once we do all of that, we get the error bounds as follows. The gradient error bound is proportional to, again, square root of the dimension, Lipschitz constant, but in particular, the error is proportional to delta. And the error in the model values, again, is proportional to delta squared. So you get error, the function values, error is delta squared. The gradient errors are of size delta with some constants that depend on things like the Lipschitz constant of the function and so on. So that's what we get linear models with finite differencing. So if we look at what we've got so far in terms of local linear approximations for the objective, well, we've got two. We've got just a straight linear Taylor series, which obviously we're not interested in, but it's a very natural choice that we could choose. Or we could do this finite differencing derivative-free model where our perturbations are of size delta. So our model in both cases is linear, either with the true gradient or with our finite differencing gradient. Our error in the model is going to be proportional to delta squared. And for the Taylor series, our standard Taylor error bound from Lipschitz gradients also gives you delta squared. You can think of this as the H goes to 0 limit of the finite differencing case. The model error, again, in both cases is of size delta squared. And that just comes from how the function's gradient changes over time, how it deviates from a linear function, and plus any errors from the gradient approximation. And we've also got our gradient errors. For the Taylor series, that gradient error is 0. For the finite differencing, that gradient error is of size delta K. And these model errors hold for all y inside our trust region, for all perturbations of size at most delta. So these are two of the kind of, let's say, very basic linear models we might be able to construct. But I want to show that the model errors are of size delta squared. The gradient errors are potentially up to size delta. So given that, that's going to motivate the next definition. So what we're going to do in our generic algorithm is we're not going to assume a linear approximation. We're going to assume a quadratic approximation because quadratic in practice is much, much better than linear. So we're going to assume a quadratic model, but we're going to construct this in some derivative-free way. We're not going to use true gradients and quasi-Newton Hessians or true Hessians. We're going to use some derivative-free mechanism to do this. And what we're going to assume is that our model is sufficiently accurate. And what that's going to mean is something that term from this 2009 paper called fully linear. Now, to be clear, fully linear doesn't mean the model is linear. It means that the error bounds are comparable to a linear Taylor series. So the model here is still quadratic, but the error bounds are proportional to what you would get from a linear Taylor series. So what we're going to ask in our algorithm is that when we build our model at iteration k to approximate the objective near xk, well, what we're going to say is that, like we saw before, the error bound in the function values, as long as we stay in our trust region, is proportional to delta squared. The error bounds on our gradients at xk are proportional to delta, and there's going to be some constants that come up that's going to be independent of the iteration we work with. So we want to be able to construct something that matches a linear Taylor series, matches finite differencing linear model accuracy. So for now, we're just going to assume that somehow we magic up a quadratic function that satisfies these fully linear approximation bounds. The last kind of, 15, 20 minutes of today, we'll talk about how we actually achieve that. But for now, I'm just going to magic up a quadratic function that in principle is going to be constructed without gradient information, just from function values, that satisfies these two error bounds. So order delta squared errors in the functions, order delta errors in the gradients. But importantly, delta appears in both. So linear Taylor series, finite difference in gradients satisfy this if we set the Hessian to be 0, the model Hessian to be 0. Okay, so now that we've got that, what we're going to do, well, we've created a local quadratic model in some way. And now we're going to do a trust region step. We're going to minimize our model, evaluate the new point at the step, accept and reject based on how well that evaluation goes, all the kind of standard trust region mechanisms. The problem that you run into if you try and prove convergence for this really boils down to the fact that in this derivative-free situation, the trust region radius, delta K, has too much work to do. It's got too many roles it has to fulfill. It's overloaded. So importantly, it really has three important jobs in this algorithm. In the derivative-based case, it only has one job. So the first thing it does is very obvious. It's the trust region radius. It's the thing that controls the radius of the step, the radius of the ball we're working in. So delta is a measure of how accurate, the region over which we expect our model to be accurate. It controls the length of the step. That is true in both the standard trust region method and in the derivative-free case. However, the extra thing we have to worry about, the first extra thing, is that delta is also our measure of model accuracy, both in terms of function values and in gradients. In the standard Taylor series case, for example, delta does affect the model accuracy for function values, but it does not affect the model accuracy for gradients. And rounding errors and these sorts of things typically don't factor into the gradient errors either in terms of delta K. So delta K has more work to do as a measure of model accuracy, which is somewhat decoupled as a role from the length of the step. The other thing that we end up needing delta for is for termination. So we'll talk about this more later, but we can't, in a normal derivative-based algorithm, you would stop when your gradient gets sufficiently small within some tolerance. In the DFO setting, we do have a GK, we do have an approximate gradient, but we can't terminate when that approximate gradient gets small because the error in that approximate gradient is proportional to delta. So if the norm of G gets small, but delta is large, then there's no guarantee that our true gradient is small. So we can't just terminate on the norm of G because delta K affects the error in the norm of G. So instead, what we do in practice, and I'll mention briefly why this is theoretically sensible, is we actually set a minimum trust region radius. And as soon as delta drops below that, we call that a termination condition based on model accuracy, based on sufficiently accurate, but that's sort of a successful run of the algorithm. So delta K has too much work to do compared to the derivative-free case. What this is going to mean is that there's going to be one small modification to the trust region algorithm. So perhaps given this, it is surprising there's really only one small change we need to make, and it's called a criticality check. So criticality here is a term I mean as a metric of convergence. So in the derivative-based case, the criticality metric might be the norm of the gradient. It's some measure of how close we are to a solution. So with all this context, this is what a basic model-based algorithm looks like. So at one iteration of it. So we're given our current iterate xk, our current radius delta, and somehow we're going to build a fully linear model. Fully linear model that's probably going to be quadratic. We're then going to calculate our step. So we're going to minimize our model inside the ball of radius delta, at least approximately to get our step. We're going to evaluate our point at the new iterate and construct this trust region ratio that measures how much did we decrease the function versus how much did we expect the function to go down based on the model. And the step is calculated to ensure that the denominator here is positive because we've decreased m. So once we've calculated our ratio, we've got our step, we now make a decision, is this step any good or not? And we update delta. And this is what it looks like. So compared to what I mentioned yesterday, the blue stuff is new. The blue stuff is what's extra that you need in the derivative-free case that you don't need when you have true gradients. So firstly, if rho is large, close to 1, then I call this very successful. We're very happy. We'll take the step. We'll increase our delta. It's successful if rho is reasonably positive, but not too close to 1. So we'll still take the step, but we won't increase our radius. If rho is small or negative, then we're unhappy. We'll stay still and we'll shrink delta. The only change that happens is we have to introduce some positive scalar mu, typically very small, and we only allow a step to be taken if the approximate gradient, if our model gradient is large relative to delta. If our model gradient is small relative to delta, that's our flag that I mentioned in terms of termination. The algorithm, the model, right now thinks it's close to a solution. It thinks the model gradient is small. But if delta is large, that means that there could be a large error in our measurement of the norm of G. So the algorithm thinks we're close to a solution, but we can't be sure because the errors are too big. And so what we do is if the norm of GK is too small relative to delta, we always shrink delta. We never take a step. We always shrink delta regardless of the value of rho. Even if we've got a really good step, we do not take it. We shrink delta to improve the model accuracy. So using that fully linear condition, we shrink delta, force our model to be more accurate, in which case where either the norm of G starts getting large again, or the norm of G stays small and delta is small, in which case we're very happy, because that means the model thinks it's close and we know that close to a solution, and we know that the error is not too big. From a practical point of view, though, what this means is we can check this blue condition immediately after we've built our model. So actually, if we build our model and the norm of G is too small, we can skip the step calculation and evaluating F and go straight to an unsuccessful step. You don't actually have to go through the process of calculating the ratio. So in practice, that's sort of a more efficient way of implementing this. But this is the really important thing that we have to check. This is called the criticality check. So as I say, if norm of G is too small relative to delta, all we're going to do is shrink delta. We're not even going to try and calculate a step. So if the algorithm thinks we're near a solution, we're going to improve our model accuracy to make sure that that is in fact the case. So this is our full basic algorithm that's sufficient to prove convergence for. The last thing I want to mention from an algorithm point of view is the step calculation. So all I've said so far is that we have a quadratic function. It's going to be a non-convex quadratic subject to a ball constraint, and we somehow want to minimize that. So in general, this is the trust region subproblem. It has this form here. There's minimizing a quadratic function. I've deleted the constant because that doesn't affect anything, subject to this Euclidean ball constraint. This is the 2 norm, and that is quite important. So this is the problem. Now, it is a non-convex problem because there's no reason that H here is going to be convex. In fact, it usually won't be. So despite the fact, though, that it's a non-convex quadratic problem with convex constraints, we can actually relatively easily write down a characterization of global minima for this problem. So it's got a bounded feasible region, so a global minimum does exist. And so the theorem that you get, and there's a great textbook here that has a proof of this, you get an if and only if condition for a point being the global minimizer. And the two things that you need are that we have the KKT conditions being satisfied. So there's going to be a Lagrange multiplier lambda associated with our constraint. You normally write it by squaring both sides. And you need the Lagrangian is stationary, which boils down to the steps solving this particular linear system. You need feasibility, you need dual feasibility, so lambda has to be greater than or equal to 0, and complementarity, so either lambda is 0 or the norm of S is equal to delta. So either lambda is 0 or you're on the boundary. So those are the KKT conditions, so you definitely need those. But on top of that, you need the matrix that comes out of this linear system to be positive semi-definite. If it's positive semi-definite, then you have a global minimizer, not just a KKT point. If this matrix is positive definite, so invertible as well, then this minimizer is unique. So this is unusual. It's a non-convex constrained optimization problem with a simple characterization of global minimizers. So there is hidden structure here that makes this amenable to this kind of analysis. But this actually is enough for us to write down a reasonably practical algorithm for solving our trust region problem to global optimality. So there's a few cases we have to consider. The first thing we try and do is we try and imagine the case where lambda is equal to 0, so where our constraint is inactive. What that's going to mean in terms of the definition of S is S just solves this Newton-type system, and we're also going to require that norm of S is feasible, so it's inside the interior, and we've got a positive definite H. So it's possible in some cases that this step, that negative H inverse G satisfies all these conditions. In that case, that particular S is the global minimizer. Often that's not the case though, and we've got to worry about the case where lambda is strictly positive. So S is given by the matrix being H plus lambda I, not just H. And this is a boundary solution. So if lambda is going to be strictly positive, complementarity means we have to stay on the boundary. And the stationarity of the Lagrangian says that S solves this particular linear system that depends on lambda. This is just a 1D root finding problem in lambda, because lambda is just some positive scalar. Given lambda, you solve this linear system, compute its norm, and you want that norm to be equal to delta. So there is one equation in lambda that you need to solve, which in principle you can do. You've got to solve this linear system a bunch of times, but in principle you can do it reasonably easily. If you've got an eigenvalue decomposition of H, this is even faster. The only thing that doesn't get covered from these two cases is what's called the hard case. This is relatively unusual to occur. This is a case where H is negative semi-definite and the vector G is orthogonal to the eigenspace associated with the smallest eigenvalue. What happens in that case is that the lambda is going to be the negative of the smallest eigenvalue, which is going to be a non-negative number or a positive number. Then you get the linear system that comes out is going to be singular, but it's going to be consistent. So there's infinitely many solutions. And of those, you pick the solution that lies on the boundary of the trust region. This is relatively unusual, but any practical solver has to be able to cope with it. In the end, though, you can, in principle, write an algorithm based on all of this. And for relatively low dimensional problems, it's not too bad. This works reasonably well. And my experience is spending this extra effort to globally minimize our model, to globally solve the trust region subproblem, does actually help in terms of practical performance. However, if the problem gets larger and from a theoretical point of view, we don't have to do all this work. Approximate minimizers of our model, approximately solving this trust region subproblem is acceptable. So I want to mention that very briefly now. So aside from solving to global optimality, the simplest thing we could do is to solve to a very low level of accuracy, which is called the Cauchy point. Well, the Cauchy point comes from just applying one iteration of steepest descent with exact line search to our problem. Essentially, that means that the step we're going to take is just a negative constant times the gradient, because if we start from 0, s equals 0, the negative minus g is the negative gradient, where this step size alpha is chosen to be the one that minimizes the model globally, subject to the constraint that we stay inside the trust region. And now this is a 1D quadratic function, so it's quite easy to write down an explicit expression for alpha c. Basically, if along this direction the objective is a convex quadratic, well then either you're going to be at the global minimizer of the quadratic or you're going to be on the boundary. If it's a non-convex quadratic, then it's sort of concave, in which case you must be at the boundary to solve this problem. And so you can write down an explicit expression for alpha c covering those two cases. In effect, there's three cases. There's convex interior, convex boundary, non-convex boundary. If you work through the calculations of all of these, what you can prove is that this particular step does decrease the objective function. It's feasible, and it decreases our objective function for the step calculation by at least this value. So this is like a norm of g times the minimum of delta times something related to the norm of g again. And this is a really important value. This all arises from trying each of these three cases separately is how you get this expression. But this is a really important expression. This is the assumption that we use from our theoretical point of view. We say that no matter how we implement our model-based algorithm, anytime we solve the trust region subproblem, the amount we decrease the model by is at least this amount. Our step is at least as good as the Cauchy point. Obviously, the global minimizer is at least as good as that by definition, but this is the bare minimum required by theory. In practice, I wouldn't use it, though. You want to do something better in practice. So what's in between? So in between this Cauchy point, the bare minimum, and a full-blown global minimization, the simplest thing to do is to use a variant of the conjugate gradient method. So I expect most people here know what this is, but CG is from numerical linear algebra. It's an iterative algorithm for solving symmetric positive definite linear systems. And the way it does it is by doing a specific form of first order optimization to this quadratic function, which corresponds to a trust region subproblem, except there's no constraint. And it only works if H is positive definite rather than any symmetric H. So that's what CG does. What you can do, though, is just run CG anyway. We're trying to solve a problem that looks like this. H might not be positive definite, and we've got a constraint, but the objective is still the same. So let's just run CG for our problem, starting from s equals 0. And there's basically three things that can happen. The first thing is we run all the way, and CG terminates, and we've solved our linear system. That corresponds to the situation of an interior global minimizer. Otherwise, what could happen is as we start running CG, at some point we move outside our trust region. In that case, what we're going to do is we're going to shrink the step that we took so that we stay inside the trust region. Basically, we stay on the boundary, and then we'll stop running things. The other thing that could happen is that we implicitly assumed H is positive definite. In practice, H might not be for the trust region problem, so we might detect some negative curvature. In that case, we know that our objective is unbounded below, and so we follow this direction of negative curvature until we hit our trust region boundary. So this is very easy to implement, very straightforward. It only requires Hessian vector products. It works for large-scale problems, and in practice is a reasonable choice. And actually, this always achieves the Cauchy decrease as well. The first iteration of CG always gives you the Cauchy step. This is a good intermediate value. Okay, so that's our algorithm. We've got our step calculation in some way, but it just provides sufficient decrease. We've got our algorithm with fully linear models and our criticality check. So for the next part, I'm going to prove that this works, prove that this converges. So this is what our algorithm looks like. Again, we're building our fully linear model, calculate the step that achieves Cauchy decrease, evaluate f, calculate our ratio, and update things based on that test. And mathematically, what we're going to need for convergence is assume that our gradient is Lipschitz continuous with constant L. F is going to be bounded below by some constant globally. Our step calculation always achieves the Cauchy decrease. We're also going to have to assume that the Hessians of our local quadratic models are always uniformly bounded. That is a technical assumption. In practice, we don't check it, but it is necessary for convergence. If the norms of H grow unboundedly, the convergence theory deteriorates rapidly. It doesn't cease to exist, but if H grows rapidly, it does become non-convergent. Well, there are counterexamples to convergence. Okay, there's 3 steps towards convergence. The first one basically says, if we're at any given iteration and delta is small relative to the estimated gradient. So if our trust region is small relative to the gradient, C0 is some complicated constant, then we're guaranteed a very successful iteration. So we're very happy we take a step. So rho is close to 1 and this criticality measure is satisfied. So that's the first result we need. If delta is small relative to the gradient, then we have success. Proof of this is relatively straightforward. Basically, we choose C0 to guarantee this to happen. So C0 is constructed so that delta K is less than or equal to C0 times GK. C0 is less than 1 over kappa H being our upper bound on the Hessian. So that means delta is less than the norm of G over norm of H plus 1. Our Cauchy decrease had exactly that expression floating around. So the Cauchy decrease condition says that our decrease in the model has to be at least, in this simplified world, at least the norm of the gradient times the current value of delta. So that's what our Cauchy decrease tells us. Then what we can do is we can estimate the value of rho k. And specifically, we estimate how close does rho k get to 1, which is kind of the optimal value. Well, if we rearrange what rho k minus 1 is in terms of absolute values, we've got a whole bunch of differences. We've got 2 differences of function values relative to the model in the numerator. We've got our model decrease on the denominator. The model decrease is bounded by half times the norm of G times delta. That was our Cauchy decrease condition. The numerator has 2 model error values, and our model errors are proportional to kappa times delta squared. That's our fully linear assumption. So if we work with that, the delta squared cancels with the delta. Then we're left with a delta divided by the norm of G, and that gives us another constant of C0 coming from our assumption here. And we chose C0 to be small. In particular, we chose C0 so that this 4 times kappa times C0 is less than 0.3. That's where this constant comes from. That's how it gets back solved. So that means that rho k is close to 1. Specifically, it's no more than 0.3 away from 1, which means it's at least 0.7, which is our success criteria. The last part, that the criticality step is satisfied, comes from the fact that we've got a 1 over mu here in the definition of C0. So that's straightforward. But this is the key idea. If delta gets small, then we're guaranteed success. And you can imagine how this translates into the derivative base case as well. This is following the basic idea that as you shrink delta, your model is accurate. So decreasing the model decreases the function. The next step is to use this result to look at the situation where we haven't converged. So let's suppose we run our algorithm for capital K iterations. And for that whole time, the norm of the gradient never gets too small, never drops below epsilon. What we can show is that if the norm of the gradient never gets small, then the trust region radius is never going to get too small. In particular, it's not going to drop below this threshold, which is approximately of order epsilon. And the way this works is by contradiction. So what we do is we consider a step where we do drop below the threshold. So I'm saying it's going to stay above. So let's say it doesn't. Let's say it drops below this threshold. Well, the only way that can happen is if we started above it and then we dropped below it. And the only way that happens is when we shrink delta, and we shrink delta on unsuccessful steps. However, our last result said if delta is small, then we're guaranteed success. So if we've had an unsuccessful step, that means our delta must be large relative to the norm of G. That's what we're guaranteed. What this is going to mean is if we go to our fully linear error bound, we're assuming that the norm of the gradient is bigger than epsilon. The norm of the gradient can be written in terms of the norm of our model gradient plus an error term. Norm of g is less than a constant times delta. The model error in the gradient is proportional to delta. And so we have that delta is bigger than some constant times epsilon. And everything is constructed so that we've proven that delta is bigger than order epsilon, but we've also proven that delta k is not too big. In particular, delta k is bigger than this threshold. However, if delta k was bigger than this, and then we had an unsuccessful step, so we halved it, then we can't have dropped it below delta min because we've added a half factor in here. So we've basically ensured that as we start decreasing delta, eventually it's going to jump back up again because of success. So there's a lower bound that we can't drop below. And that becomes because we're decreasing by a factor of half each time. But the key result, as long as you haven't converged, delta remains big. That's the key outcome. And that leads us to the main convergence result. So what we're going to do is we're going to do the same thing. We're going to assume we're using capital K iterations and we haven't reached a good point in all of those K iterations. And what we're going to do is try and upper bound how long that can last for. So what is an upper bound on capital K? The way we're going to do this is we're going to look at the good iterations and then the bad iterations separately. So I'm going to split up all my iterations into the successful ones where we took a step and the unsuccessful ones where we did not take a step. And I'm going to note that we know that delta never gets too small. Okay, so first let's look at the number of successful iterations. So how big can that possibly be? Well, we've got our Cauchy decrease and our criticality check. So that says that, for every iteration, but in particular for successful iterations, the decrease in our model is at least our Cauchy decrease condition. Now, delta is bounded below by delta min, because that's what we know from our previous lemma. But the criticality check says that everything with a norm of g in here is also bounded below by something to do with delta. So every time we've got a norm of g, I can replace that by mu times delta min, times the lower bound. And the norm of h I can replace by this upper bound. And what this all together means is that the decrease in the model at every iteration, at least for successful iterations, because this criteria only occurs for successful iterations, this criticality check. For successful iterations, the model decrease is at least proportional to delta min squared. So delta min is order epsilon. The decrease is proportional to order epsilon squared. What this means is if we've got a successful step, that means that the true decrease is at least some fraction of that decrease because rho was at least 0.1. And that means that the true function also decreases by a constant proportional to epsilon squared. So we know for every successful step, we've decreased our objective value by at least this constant. And this constant is independent of k. So all we do is we start summing. We say, okay, over the course of k iterations, we've decreased our function by a certain amount at each step. So let's just add up our total decreases. But the total decreases only come from successful steps. On unsuccessful steps, we don't change x, so there's no decrease from those. So the total decrease we achieve can only come from successful steps. And the decrease at every successful step is proportional to delta squared. So the total decrease is this constant times the number of successful steps. All we need to do is note that we can't keep decreasing our function forever. We've assumed that there's a lower bound on f, which means that there is an upper bound on the total decrease we can achieve. So at every successful step, we decrease our function by a constant. Our function can't decrease forever, which means there's a cap on how many times this can happen. In the end, we get a bound that says the total number of successful steps we can possibly achieve can't be more than order epsilon to the -2 successful steps. And that order includes things like how close our starting point is to the lower bound. So we've got a bound on the number of successful steps. Now we need to bound the number of unsuccessful steps because we're partitioning k iterations to successful and unsuccessful. For unsuccessful iterations, we track what happens to delta. So over the course of our iteration, we know that delta never gets too small. We also have our updating rule. Our updating rule says if we're doing well, we increase delta by at most a factor of 2. Sometimes we keep it constant, sometimes we double it. So we increase it at most by a factor of 2. If things are going badly on unsuccessful steps, we halve delta. So we start at some initial value. We go through a mixture of doubling and halving, depending on how many successful and unsuccessful steps we have. But overall, it never gets too small. That means we can't have too many halving steps relative to how many doubling steps we have. And that's what we piece together. So aggregating this over k iterations, the final value of delta can't drop below our critical value, but that final value of delta says, let's start from our initial value, double it every time we have a successful step, halve it every time we have an unsuccessful step. So we get this inequality here. And if we look at delta min, SU, and delta naught, we can get an upper bound on the number of successful iterations relative to these other constants. Delta naught divided by delta min is a constant. Number of successful iterations we've already bounded. So again, the size of U is roughly proportional to the size of S. So again, the number of unsuccessful iterations is at most epsilon to the -2. So altogether, this gives us a global convergence result. So it says under all of these assumptions, we're guaranteed that for any epsilon, we're guaranteed that at some point, the norm of the gradient will drop below epsilon, and that will first occur after at most order epsilon to the -2 iterations. Corollary of that is that the lim-inf of the sequence of gradients goes to 0. So there's a subsequence of gradients that go all the way to 0. With more work, you can prove that the full sequence of gradients goes to 0. So the lim-inf becomes a lim, but I'm not going to prove that. That proof is very different and not particularly informative. So the full sequence of gradients does go to 0, and we have to wait at most epsilon to the -2 iterations to get it to drop below epsilon for the first time. So that's our result. One question I raised yesterday is, how does this compare to derivative-based methods? We've gone from having gradients to not having gradients. Is there a penalty? What does this bound look like in the derivative-based case? Is there a penalty from losing derivative information? What happens here? So I should say the dependence on epsilon to the -2 iterations for a non-convex problem. Some of you may know this. This is completely standard when you have exact gradients. There's this nice book from 2022 that has this epsilon to the -2 bound for line search methods, for derivative-based trust region, for various forms of regularization. Unless you assume more about your problem, epsilon to the -2 is pretty much all you can get. So this is totally standard. However, there is a penalty for losing access to derivatives, and that comes from the constant that's hidden inside this big O. So if I expand things out, let's use kappa m here to mean the largest of our fully linear error bounds. Then what you get is if you've got a gradient-based trust region method, the constant is relative to the model error plus the Hessian upper bound. For derivative-free, it's that constant, the kappa m plus kappa h is now squared, and there's an extra factor of kappa h out the front as well. So the constant is worse. The reason that constant is worse basically comes from the Cauchy decrease condition in successful steps. For successful steps, we bounded the Cauchy decrease using the fact that the norm of G is bigger than mu times delta min from the criticality step. In the derivative base case, the norm of G is equal to the norm of the gradient, which is just bigger than epsilon. And epsilon is much bigger than mu times delta min by definition of how it was constructed. So the Cauchy decrease is going to be larger in the bound on the Cauchy decrease at least is larger for the gradient-based case versus the DFO case. So there is a penalty that comes in this constant when we move to the derivative-free case. And we'll mention it later, but kappa m is usually larger for model-based methods as well. So the kappa m for gradient-based is usually basically just the Lipschitz constant of the gradient. For derivative-free things, there's a Lipschitz constant, but there's usually explicit dependencies on dimension as well. And the last thing I want to mention, I mentioned before, is termination. So we don't know the norm of the gradient, so we can't in practice terminate when that gets small. So what are we going to do? Well, in practice, there's really two ways we terminate. The first way is after some maximum allowable budget. Usually that's going to be measured in total number of objective evaluations rather than total number of iterations, because we don't do the same number of evaluations at every iteration. So the cost per iteration can be more variable than in gradient-based methods. So that's just a standard, some kind of finite termination property. The other one, which is sort of our optimality condition, is when delta gets small. That's why I mentioned before, we can't terminate on the norm of G because the norm of G has errors of size delta. So instead, we terminate when delta gets small. And the reason that that's a reasonable thing to do is this result. So the first thing we can prove for this algorithm is the sequence of deltas will go to 0. The full sequence of deltas will go to 0. So we're guaranteed that we can, in fact, terminate when this is small. But also, when delta drops below some threshold for the first time, we're guaranteed that at that point, the size of the gradient we're terminating on is not too big. It's proportional to the size of that tolerance. Now, again, there are constants in here that depend on the various kappas and so on, but at the very least, this delta min, the tolerance that we terminate on, does track the optimality condition of where we stop. So that basically justifies that terminating on small delta is in fact a sensible thing to do. Okay, last thing I wanted to mention is model construction. So we've got an algorithm that somehow assumes we can magic up a fully linear model in some way. Once we've got that, we can calculate our step using the methods I mentioned, and then all this theory works. So the one ingredient we haven't really spoken about is how do we construct our model using interpolation, essentially, by sampling a function values. So we need to be able to construct fully linear models at every iteration. The way we're going to do that is by doing interpolation. So we're going to sample points near xk, and we're going to do either linear interpolation or quadratic interpolation to define our model. If a model is close to a Taylor series, then it's going to be fully linear. This is going to be kind of the key ingredient for our analysis. We're going to construct an interpolation model that is going to be a good approximation to the Taylor series. The Taylor series is already fully linear, so the full thing should be fully linear. And in fact, we do get exactly this result. Let's suppose we construct a quadratic model that is a good approximation to a first-order Taylor series, and the error is at most size delta squared. If that is true and the Hessian is not too big, then the model is fully linear and the constants relate to this proportionality constant in here. So our goal is to produce a model that's going to be quadratic that is close to a linear Taylor series in magnitude. That's going to be our goal. So to start with, let's do linear interpolation again. We've looked at finite differencing. This is going to be a slightly more generic version of that. So let's say we want to construct a linear model, and now I'm going to assume the constant is up for grabs as well. So we've got a constant and a model gradient to fill in. So we've got n+1 degrees of freedom in our model, which means, let's call it p, which means we have to sample the value of f at p different points. So y1 up to yp, where we know the value of f. Then if we say, well, at these p points, I want to guarantee that my model matches the known function value, I end up with a p by p linear system to solve for c and g that looks something like this. So the matrix depends on the locations of my interpolation points. The right-hand side depends on the function values that I'm trying to fit to. So a simple p by p linear system, p is of order n. We can just solve this. There's no particular structure here. This is not like symmetric or sparse or anything in general. So you just have to use like a direct solver. What we will find though, in a couple of minutes, is that we want the distances between our interpolation points and our base point, our current iterate, to be of size delta, which kind of makes sense. We're trying to approximate our model inside the trust region. So our interpolation points should be pretty much within the trust region, or at least close to it. However, I just told you that delta goes to 0 as the algorithm progresses. So what this means is that this matrix becomes increasingly ill-conditioned. We've got a column, the first column stays order 1. All the remaining columns decrease to 0 as the algorithm progresses. So this matrix becomes approximately singular. As we progress, we get ill-conditioning coming in. So the first thing we have to do is get rid of that ill-conditioning. And what we do is we say every time we have an interpolation point, well, let's shrink that distance to xk by a factor of delta. Let's get rid of that delta goes to 0 aspect. I'm going to call that s hat. This is like my scaled perturbation. I now use this inside my interpolation linear system. I'm now solving for delta times g rather than g, but now I don't have this situation where the columns of m are going to 0 as we progress, and I can just divide by delta at the end to get my g. So now, is m hat ill-conditioned? We know that norm of m is never going to get too large because the norm, because if all the points are of size delta away from xk, that means the norm of the s hats is all going to be approximately 1. So the norm of m never gets too big, but the norm of m inverse may still get large. So if all the s's, for example, point along a subspace, for example, this matrix can still be singular. So we can still get ill conditioning, even though the points aren't collapsing and we don't get it from the scaling. And that's going to be reflected in the fully linear error bounds. So the norm of m hat is going to come into our error bound, and the distances these points stay away from the base point is also going to come in as well. And so what the result ends up looking like, conscious of time, I'll try and jump through this, but we can say that if all our points are of order delta away from xk and m hat is invertible, then we get a fully linear model where the model constants of the error bounds depend on the size of this beta. They also depend on the norm of m hat inverse. And there's, again, Lipschitz constants, explicit dependencies on dimension coming through. I'm conscious of time, so I don't think I have time to go through this proof. But basically, the important thing that we're going to do is we're going to prove this, we first look at the Taylor error bound at an interpolation point, because we know the function value matches the model value at the interpolation point, and we can just use Taylor's theorem to bound that error. So we measure the error at our interpolation points, and if we want to measure our error elsewhere at a non-interpolation point, we use this result here that allows us to write the perturbation, the scaled perturbation, in terms of the scaled perturbations of our interpolation points. So we construct a V that solves this linear system, but basically we construct our Y as a linear combination of the perturbations that gave us our interpolation points. So the vector of 1 and y minus xk is written as a linear combination of 1 and yt minus xk. So it's a linear combination of our interpolation points. Once you do that, and we can get an upper bound on V based on the norm of m hat inverse here. Once you go through all that calculation, the error between our interpolation model and the Taylor error is controlled by an order delta squared term, and this V appears, the one norm of V appears in here as well. So V again is how do you represent my current point that I care about, Y, as a combination of my interpolation points. That gives us our V. So that's purely a geometric, essentially, consideration. And then we've got an upper bound on V, and all these results will give us the bound, but I don't have time to go through all of those details. But we can use an example. If we go back to the example I mentioned before, finite differencing with step size delta k, that is equivalent to linear interpolation with this particular interpolation set where we have the base point and perturbations of size delta k in each coordinate direction. So that should be En. If we do that, we can compute our error bounds. Our fully linear constants are order the square root of n. If we plug this into our main convergence result for our algorithm, we can see that we get our optimality error epsilon after at most n times epsilon to the minus 2 iterations, n being the dimension of the problem. At every iteration, we have to evaluate n plus 1 points. So that means overall we need n squared times epsilon to the minus 2 evaluations, which is the important thing for DFO evaluations, to drive the error below epsilon. This can be improved a little bit if we scale our perturbations to be delta over square root of n. Then the dependency on n decreases to what I expect is optimal, but I'm weirdly unable to find a good reference for this. I'm not sure whether it's been able to be proved because it's surprisingly tricky to prove. But if you do that, you get order epsilon to the minus 2 iterations, no explicit dependence on n. Number of evaluations is just proportional to n. And this is basically what you would get in a gradient-based case. There's no explicit n in a number of iterations, and you sort of get one gradient evaluation per iteration. And it seems reasonable to say that one gradient costs about n function values because that's the amount of information that you get. So that's how you can get linear interpolation. Quadratic interpolation is better, though. Linear models are not particularly good. There's at least one case where that's not correct. I'll mention that tomorrow, hopefully. But generally speaking, you want to use quadratic models. If you want to build a fully quadratic model, then you need more degrees of freedom because you've got a full Hessian to build, but the Hessian is symmetric. So you have like order n squared over 2 degrees of freedom in H. So you need roughly n squared over 2 degrees of freedom, number of interpolation points for quadratic interpolation. You can do this. There's all the theory follows exactly as before, but you do get better error bounds. The problem is you need a lot of interpolation points. You need order n squared interpolation points. And the cost of solving your linear system, well, it's a p by p linear system. So order p cubed work to solve linear systems. So order n to the 6th work for solving linear systems, which can rapidly become a problem. You do get higher accuracy, though. So this can be useful, particularly if n is not too big. But in practice, what's really good is a middle point. So we say linear models usually aren't good enough. So the number of interpolation points we want is usually going to be bigger than n plus 1. But normally, order n squared over 2 is a bit too many. So a midpoint of what I would call underdetermined quadratic interpolation is usually a good choice. So I want to fit a quadratic model but I haven't got enough interpolation points to uniquely specify what it is. So I have to add in some extra information to say which of the infinitely many allowable quadratic models, so infinitely many quadratics fit our data, which one should I choose? So there's two reasonable choices that have theory associated with them that work quite well. One is you take the minimum norm solution of the linear system, so like a pseudo-inverse of the interpolation conditions, something like that. That works perfectly well. The one that I have used a bit more and is sort of involved in the more practically successful codes is called minimum Frobenius norm interpolation. So I'll call that MFN. So MFN is sort of more widely used in the top codes. The way this works is we say, okay, let's construct a quadratic model that's guaranteed to fit our interpolation points of all the ones that we have, all the P ones that we have. Let's ensure our Hessian is symmetric. And of those infinitely many valid quadratic models, pick the one that minimizes the norm of the Hessian in the Frobenius norm, because that's much easier to solve for. So we pick, of all the possible interpolation models, pick the one with the smallest Hessian. In practice, you could use the minimum change in the Hessian, and that works very well, but there's no theory associated with that. And this is sort of motivated by quasi-Newton updating. For those of you that know how quasi-Newton rules are constructed, they do something very similar. It's given the information we already have, find me the smallest Hessian or the smallest change in the Hessian that meets all the information that I want. This becomes a convex, equality constrained quadratic program, this problem for finding C, G, and H. And so that boils down to being solved in a linear system of size P plus N plus 1. It's got a symmetric saddle point structure for those of you that care about numerical linear algebra. And this does generalize. If you send it all the way to N plus 1 or all the way to N squared over 2, you do recover the linear and fully quadratic interpolants. So this kind of generalizes those two extreme cases. I won't go through the theory. I don't have a proof of this, but the main thing that you get out of this is that, again, as long as your interpolation matrix is invertible and your points are not too far from xk, then you can prove fully linear error bounds that, again, have something to do with the norm of the inverse of the matrix. This is the pseudo-inverse of the linear regression matrix that comes out. You get explicit dependencies on dimension and beta and all of that, but you also get an upper bound on the Hessian. You can actually you can explicitly bound the size of the Hessian, which, because we require for our algorithm a uniform upper bound on the Hessian, this is actually quite good for us. So we can use this inside our convergence theory for the full algorithm because we needed something like this. As an example, P equals 2n plus 1 is a rather popular choice in practice. And the simplest way to get an interpolation model of size 2n plus 1 is to take our base point and plus or minus the n coordinate perturbations. Obviously, we can do this in other ways, but this is a very simple way of doing it. The model you get from doing minimum Frobenius norm interpolation corresponds to doing central finite differencing for the gradient and using the standard 3-point stencil for second derivatives to get diagonal entries on the Hessian. So you get standard finite differencing rules from this particular MFN construction. And if you do that, with a little bit of work, you can show that kappa is order 1. The bound that I showed you just before doesn't give you that. You've got to be a little bit more careful. And you can get explicit bounds on all your various values of kappa. And you can recover that explicit dependency on dimension that I showed you for linear interpolation. But you've got more information. So in practice, it's going to work better. But in theory, you recover the same bounds. And again, we can do some rescaling to reduce that dimensionality dependence if we want to do that. Okay, so those are kind of the three big constructions. I'd say MFN is the most popular choice in practice in terms of balancing theory and practical success. So that's all I wanted to say today. This is a very simple approach to model construction. At xk, with a current radius delta k, we pick points of a certain structure inside that ball. What that does mean is that we're very wasteful. If it says at every iteration, we basically throw away all the function values we had before, and we pick a completely fresh new interpolation set. This gives us good theory, but is not good in practice. We care about when evaluations are expensive. We care about recycling information as best we can. So tomorrow, I want to look at how we adapt this to use very efficient interpolation set management, where we reuse as much of the interpolation points from the previous iteration as we can. I want to bring the number of evaluations down from order P, order N evaluations per iteration down to 1 or 2. And then we'll look at some various extensions like constraints and noise and various other things. Okay, that was everything I wanted to say for today. Got a couple minutes if you want to have questions. But yeah, that's the basic theoretical basis for what we're going, and we'll make things a little bit more practical tomorrow. So thank you. And I'll stay on for a couple of minutes if there are any questions as well.
So, Lyndon, can I just ask the question?
Yeah.
Yeah. So I just was wondering, what is the dimension that you actually can handle with such kind of problems, especially because you said smaller dimension, larger dimension. So, but what are the ranges actually?
Yeah. So typically, for most DFO problems, we're talking n is maybe order 10. You can sort of solve order 100. Once you start getting beyond that, in practice, things start to slow down a lot. So all these constants have explicit dimension. I wanted to show that in there. So it doesn't really scale particularly well once you get larger than maybe order 100. But Zaikun's talk on Thursday is going to cover, he's got approaches where you can get n is order like 10,000 or more in a reasonably practical way. So yeah, stay tuned for to see how he does it, essentially with dimensionality reduction.
Right. Thank you.
Okay, in that case, I will stop the recording and say thank you.